to an incredibly short little theorem, but very quaint and interesting one. Now, what is the claim? Let the series iterating through 1 to infinity of un of x be a function sequence defined on some open interval. On some open interval AB. Now, the openness of the interval is very important and will come up in the proof. It matters, right? Now, also, let un be continuous on the open interval AB, and let the series iterating through 1 to infinity of un of x converge uniformly on AB. Then, function capital F of x, defined as at each point as the limit of the series iterating through 1 to infinity of un of x, is a continuous function, so it's continuous on AB. So essentially what we're saying is that if we have an infinite sequence of continuous functions which converge uniformly, then they converge uniformly to a continuous function at each point. That's nice, but how do we prove it? Well, it's simple. Look, the functions sk, defined as the partial sums, the standard definition of a partial sum, I'll write it out just in case, are continuous. That is because UNs are continuous functions and partial sums are nothing more than finite sums of continuous functions, which itself must be continuous, so that's quite trivial. And we know that sk converge uniformly locally on AB. How do we know this? Well, we know this because the series converges uniformly on AB. Therefore, the partial sums also converge uniformly on the open interval AB. And since the interval is open, it also means that it automatically converges locally uniformly. So we know these two facts, and therefrom we easily obtain by the more Osgood theorem corollary, which I have reminded you here. There's a little reminder box up there. It holds that their limit is locally continuous and thus continuous. The limit is limit of sk is the limit as n approaches infinity of sk, which is the limit as k approaches infinity of the series. This is by definition un of x, which is equal to the series where n iterates through 1 to infinity of un of x, again by definition, which is f of x. Hence, capital F of x is continuous, which is precisely what we wanted, which concludes the proof.